Hey, fellow mathers! Welcome to this podcast where math is figure-outable. I'm Pam, a former mimicker turned mather. Hello?
I was just thinking, are you going to say Pam or Pam Harris?
Do you remember?
And I'm Kim, a reasoner who now knows how to share her thinking with others. At Math is Figure-Outable, we are on a mission to improve math teaching.
Because we know that algorithms, while they are amazing historic achievements, they're terrible teaching tools because mimicking step-by-step procedures actually traps students into using less sophisticated reasoning than we should be using and developing.
In this podcast, we help you teach mathing, building relationships with your students, and grappling with mathematical relationships.
And we invite you to join us to make math more figure-outable. Dum-dum. All right, Kimberly, what's up today?
Well, we have the best journey group ever. Our
live coaching group?
Live coaching group. Yeah. So they ask really thoughtful questions. And I'm excited today because we have a question from Brandon that we thought we'd bring to the world. I know that you addressed his question in a group coaching session, but I think maybe there's other people in the world who are wondering about the same thing. So let's do it today.
Let's do it.
Brandon said, I really enjoyed the proportional reasoning workshop and problem strings like sticks of gum. So if you are a longtime listener, you know we have some fantastic building powerful numeracy and some high school workshops. So this is one of them that he took. And you've probably heard of some of our sticks of gum problem strings. So he's loving those. And he says, I've been thinking a lot about helping students see the relationships for y equals kx. What would y'all suggest? I feel like sticks of gum and many proportional reasoning strategies have to do with scaling, but don't necessarily focus on the relation between x and y.
Yeah, nice. It's a great question, Brandon. And let's dive into that. So if you can picture a lot of the ratio table problem strings that we've done, if I say something like, I've got a pack of gum and it's got 27 sticks, then I might draw an input-output table where I've labeled it packs and sticks, and I've got 1 to 27. And then I might ask you several multiplication or division questions based on that. So I might say how many sticks are in 2 packs. You would probably double the 27 to get 54. We're not going to actually do this math. I'm just going to talk through a little bit of it. I might say, what about 10 packs? And then you might scale times 10 and say, well, since there were 27 sticks, you'd have 270 sticks. And then I might say, how about 9 packs? And then can you use the 10 packs to find the 9 packs, just subtracting a pack? And you might subtract the 27, and I have to think for a second. Is that 243? Yeah. So now I've got some values on the table, and what I've been doing this whole time is scaling. So you'll see that I have a scaling mark between the 1 pack and the 2 packs times 2. I have a scaling mark between the 1 to the 10 packs times 10. I have scaling marks on both sides of my ratio table to do the 10 minus 1. I don't know if that's a scaling mark, but it's like a bracket to do the 10 minus 1 pack to get the 9 packs. So we're kind of scaling between values. I could say, how about 20 packs? And we could scale from the 2 packs. I could say 99 packs, and we could scale from the 9 to get 90 and then add the 9, or we could scale and get 100 packs. And all of that, those actions are kind of between the values in the, maybe I should say within. Ooh, are they within or between? They're from packs to packs, and I sort of do the same thing to sticks. Mm-hmm. So similarly, if I were to give you something like 2,600 and think for a second. If I had 100 packs and I had 2,700 sticks, and then I said 2,673 sticks, and I asked you for how many?
Did you just play Ivy Need in your head?
Yes, I totally did.
Okay.
So again, you could scale kind of from packs to packs and sticks to sticks. Either way, we're sort of scaling between packs and between sticks. What Justin? Hey, Brandon, you have a new middle name, named Justin. Sorry, Brandon. We like Brandon. He's a thoughtful guy. Brandon's asking about how do I go between packs and sticks, not just from packs to packs, 1 pack to 10 packs or 1 pack to 100 packs, but how do I go from packs to sticks? How do I help kids sort of write the equation of a line? Well, what if I gave you some random number and I didn't have anything in my table to use? Do I have some relationship I could use between the number of packs and the number of sticks? For the particular problem that I just gave you, if I have 1 pack to 27 sticks, I could give you any number of packs, and I could say, well, if I gave you, I don't know, 19 packs, you could multiply that by 27 and you could get the number of sticks.
Mm-hmm.
So that's like 19 times 27 would give me the number of sticks. And I'm just going to let the number of sticks be y. So I've got sort of 19 times 27 is y. If I asked you for 37 packs, I could do 37 times 27, and that would give me the number of sticks.
Mm-hmm.
If I had, give me another random 2-digit number, Kim.
82.
If I had 82 packs, I could multiply that by 27 and I could get the number of sticks. Now, in a ratio table, we would usually go between packs and we'd find nifty ways of getting to those numbers. But I also could just say to myself, 19 times 27 to get the number of sticks in 19 packs, or 37 times 27 to get the number of sticks in 37 packs, or 82 times 27 to get the number of sticks. So then I might step back and ask kids, what are you doing? And kids might say, well, like what's changing and what's not changing. And as if you looked at my paper right now, I have 19 times 27 equals y. 37 times 27 equals y. 82 times 27 equals y. Well, what if I had any number of packs? And I'm going to say that because then I might write down an n. What if I had n number of packs? Like any number of packs. Where does that go? Like, what's the 27? That's the number of sticks per pack. So that doesn't change. The y didn't change. What changed every time? If I gave you some random number, where would you put it? Oh, it would be that first number. So I would have n times 27 equals y, which is the number of sticks.
Mm-hmm.
N or x or whatever. Maybe I'll let it be x. I like to do ne and make it n. But if it was x, then now I have x times 27 equals y. And then I might say, hey, how do mathematicians typically write x times 27? They typically write that as 27 times x equals y, or y equals 27 sticks of gum per pack times the number of packs, and I've just written x. So Kim, if you can see what I wrote on my paper, I wrote y equals 27x. But as I wrote that, I said y, the number of sticks, is equal to 27 sticks per pack, and I wrote 27, times the number of packs, and I wrote x.
Mm-hmm. So it sounds like when you're doing those scaling proportional reasoning strings like Brandon was talking about, you can still bring awareness that in all those proportions, they're all represented by y equals 27x. Like just bringing awareness to that as you're doing that work with students, even in the scaling ones.
Absolutely. Yeah. So
Yeah.
this situation can be represented by this table,
Mm-hmm.
but it can also be represented by, give me any number of packs, x, multiplied by 27 sticks per gum in a pack, and bam, you'll get y, the number of sticks. Yeah. And so we could bring that out as you're doing I would probably do a lot of scaling first.
Yeah.
In fact, I would use ratio tables and do sticks of gum types of strings with lots of scaling in 3rd, 4th, and 5th grade.
Mm-hmm.
And then in 6th grade, when we start talking about non-unit rates, I would do the same kinds of strings but with not 1 to 27, but it would be something like, 4 pounds cost $7.87. And so then I would have the ratio 4 to $7.87. And then I would scale from there. I would do a similar problem string where I'd say, well, what if I bought 8 pounds? What if I bought 10 pounds? What if we would continue scaling with that non-unit rate and give kids experience there. And at the point where I'm ready to start saying, hey, what do we call these relationships when all these ratios are equivalent? Oh, we call that a proportional situation. Mm-hmm. If the ratios are equivalent, then it's a proportional situation. What do graphs of those proportional situations look like? That's where we're graphing the ordered pairs of those X's and Y's. Now I'm going to start to do a lot of work to try to get them to see the relationship between X and Y. So I'm going to keep scaling. We want to keep getting them better at that proportional reasoning, but we're also going to talk about the relationship between X and Y. Mm-hmm. So one way that I'm going to help students create the relationship between X and Y is doing the problem string and deriving out of that relationship. Another way that I can work on that is, Kim, will you sketch a triangle for me? In fact, leave space to sketch a couple triangles.
Okay.
So you got a triangle and one side is A and it's kind of long. Draw kind of a long, skinny triangle.
Okay.
Long, skinny
Made
triangle.
a guess. Yep.
Yeah. So long, skinny triangle.
Yep.
Not the longest side, but the next longest side.
Okay.
I don't know. Just draw an equal out. Don't draw a isosceles triangle. So three different lengths.
Okay.
The middle length is A. That's A long.
Okay.
Okay. The shortest length is 8 long.
Okay.
Now I want you to draw a triangle that looks very much the same shape that you just drew, but it's smaller.
Okay.
Now I want, do you have your smaller one?
Yep.
And do they look the same shape?
Yep.
So if I grab that little one and I stretched it on a computer so it stretched in all the directions, it would look like the bigger one?
Yep.
Okay, cool. That middle length side is 12.
Okay.
And the smallest length is 4.
And I don't know the other lengths.
No, but
Okay.
what you do know is the two triangles are similar.
Okay.
So that's kind of important. Now,
Yeah.
we haven't really defined similar triangles, but it's same shape, but the side lengths have been scaled. The side lengths are in proportion. So the ratio should be equivalent. So do you have a gut instinct on this one? What do you want to?
Like to find A?
Yeah, to find A.
Yeah. Yeah. I want to double 12.
Why would you do that?
Because the side lengths that are 4 and 8, the 8 is double the 4.
Nice.
And so like A is double the 12.
I'm going to slow you down. So you
Sorry.
said, no, it's okay. I thought, do I interrupt? And then I started to, and I was like,
Yeah.
don't interrupt, let her talk. So you said the 8 is double the 4. So on the two triangles, I've now drawn a scaling arrow from that 4 to the 8. So that's kind of between the two triangles, right? Because the 4 is on one triangle, the 8's on the other triangle. So between the two triangles, I've drawn this arrow, and you said it was double. So then I put times 2 kind of above that long scaling arrow.
Yep.
And then you said, well, if that's times 2 and A corresponds to 12, I'm putting words in your mouth, but then you also doubled that one?
Yeah.
Yeah. So that now I have the same kind of scaling arrow between the 12 and A, and I'm writing times 2 above it. So you're like, A has to be double 12, and you said it's 24. Yeah.
Yeah.
Cool. So I would then bring out to students, like, make sure that makes sense to everybody. And we would call that a between strategy, because you looked between the two triangles and said, okay, I know they're similar, so they got to be the side lengths are in proportion. So 4 to 8 has to be the same scale as 12 to A, and that was times 2. Cool. Then I would change colors, and I would say, did anybody stay within the second triangle, the little triangle? Did anybody look between the 12 and 4? Because 12 remembers the middle, the length of the other triangle. It's the one that corresponds with A. Yeah. So, Kim, if I direct your attention there, what are you thinking about?
Yeah. So I see that the short side, which is 4, is a third of the 12. So 4 times 3 would be 12, which means that 8 times 3 would be A.
Nice. So as you were talking, inside the triangle, or not inside, but like on the triangle, at the triangle, the smaller triangle between the side length of 4 and the side length of 12, I have a red arrow, and I've said times 3. And then between the 8 to the A, oh, that's terrible that I have an 8 and an A. Maybe I should have made that X. From 8 to A, then it would have to have the same scale factor, times 3. And sure enough, there's our 24 that we found before. So in 2 ways, we're really clear that A is 24. And that time you used a relationship within the two triangles. So I have 2 different colors. So I have a between strategy. It's the scale factor between the sides of the two triangles. And I have, in red, I've written a scale factor within the sides of a triangle. And then we've used that same scale factor in the other triangle. So you might be like, Pam, what does this have to do with y equals kx? Well, in a big way, we have a proportion, and we want to get kids acknowledging, realizing, constructing the idea that there is a between relationship and a within relationship.
Yeah.
And sometimes one might be easier to use than the other. And so we want kids to look at both of them.
So can I tattle on myself?
Oh, go. Yes.
So somebody asked a question in the teacher Facebook group, that we love, and good questions. Join us there.
Math is Figure Outable Teacher Facebook group. Yep.
Yeah. So somebody asked a question, and I was like, I've said I'm lazy sometimes when I read things, and I only looked. I can't remember which one. I think I only looked between.
Okay.
And I was like, gave some like answer about being an estimate or whatever, because the between was kind of like funky. And then somebody else, shot back like, oh, well, if you look within, and I was like, dang it. I totally didn't even bother. So
are you saying, that the relationship you used, the numbers were funky enough that you just estimated?
Like times 10 and a third or something between.
So you estimated, and you're like, if it's about 10 and a third, then about 10 and a third, the other one would be this. Yeah. It's close enough, whatever.
Like all these people are like, how about this way, this way, this way? Oh man.
Actually.
You got me.
So that would be a moment in class where we get the ooh factor, right?
Yeah,
where you could go, oh, wish I would have looked at that one. Yeah.
I think that's what I said. Shoot. Wish I
How
would
about
have
my
seen that.
I
Yeah.
want my brain to do that next time.
Yeah.
All right,
Yeah.
next time. So that's a good moment that we want to engender in class
Sure.
where we want kids to go, right, right. I can look within, but I can also look between. Cool. So a way that that could look for this particular problem that we just did, I could write A to 8. So like I'm going to write kind of a fraction, A over 8. And I'm only
Mm-hmm.
saying over because
Mm-hmm.
it's an
Mm-hmm.
audio podcast. And so picture the fraction A over 8
Mm-hmm.
equals 12 over 4. Because,
A
and
equals 12 over 4.
is that right?
4 over 12.
A over 8, 12 over 4. A, the letter A to 8.
Sorry. I wrote mine backwards. A
See,
right. Yes. 12 4.
I shouldn't have used A and 8. That was
That's
dumb.
okay.
So A to 8 is
Yes.
equivalent to 12 to 4.
Yes.
Okay, cool. So I could have that proportion, these two fraction looking things equal to each other. We know they're equal to each other because we started the problem saying the two triangles are similar.
Right.
That's part of what we would want to help kids to develop, is that therefore the sides are in proportion.
Mm-hmm.
So we would want kids to be able to look at that proportion, A to 8 equals 12 to 4, and say to themselves, now, I don't know, looking at it that way, you might instantly go, gee, 12 divided by 3 is 4. So what divided by 3 is 8? It's got to
Mm-hmm.
be 24. Like that's just screaming at me. But a kid also might say, yeah, but I can get from that 8 to 4, the two denominators, 8 to 4, by like half of that. Well, so then I've got to take half of something to get 12. Bam, that's got to be 24. There'd be another way of thinking about it.
Mm-hmm.
So with this one, I gave you particular numbers that happen to go either way. Often it's kind of like the one you got caught on the Facebook problem.
Yeah.
That one way is slicker than the other.
Sure.
And it might depend on the day where one relationship pings for you better than the other
Sure.
relationship. We want to encourage kids to look between both. Just like nicely done, Brandon, we don't only want kids to scale in ratio tables. We also want them to develop the relationship between X and Y.
Mm-hmm.
We want both of those.
Do you ever do a problem string with a series of these triangles where like the first one might be like this, where it's pretty simple relationships, but then you like go through the string and you end up where like one would be better than the other?
Totally. Yep.
Yeah.
Yeah. I'll also do just flat out worksheets like that, where I'll
Mm-hmm.
give them a couple, 3 or 4 triangles where the first one's pretty accessible. You can do it either way. And then there's one that there's an obvious one way. And then there's one where there's an obvious the other
Mm-hmm.
way. And then
Mm-hmm.
there's one where, neither of them are great. And you're gonna have to work for both of them.
Yeah. Yeah.
Yeah. And that would be a fine time for some independent thought. Kids are, after we've done a lot of work. Sure. I think, I wonder sometimes if people hear me and go, so is there ever homework, like independent work? Yes,
Mm-hmm.
there is definitely independent work. And that is an example of something that I would definitely have kids do and talk about.
Yeah.
And then I would want to have them share, hey, what did you choose on the first one? Yeah, everybody did the within. Hey, what did you do on the second one? Yeah, everybody did the between. What did you do on the third one?
Mm-hmm.
And then it's not who's right for which one they chose, but it's like to build the different strategies that are coming out of the two different ways you do it,
Mm-hmm.
the two different ways you would solve. And then same on the harder one, like let's share strategies. Now
Mm-hmm.
I might on a given day only do one of those. And we might just choose like the third problem where everybody had, maybe not the hardest one. Maybe the hardest one was just kind of keep kids going and really try something, but let's actually share the strategies on the one I know everybody sunk their teeth into well. That
Sure.
would be a good one to kind of share out. Okay. So there's one way, Brandon and everybody else, that we can help kids develop both the within and between relationships. So let's do another one. Kim, quick problem string. So draw a ratio table, vertical ratio table. And I wouldn't make a kid do that, but I'm going to have you do it because you can't see what I'm drawing. And I'm going to say that we're starting with the ratio 4 to 6. So I've got a vertical ratio table. On the left side is 4 and on the right side is 6. Do we have the same thing?
Yep.
Cool. All right. Then I'm going to tell you that the next thing I'm going to write down is on the right-hand side. I'm going to write an 18. And I'm going to ask you what corresponds to 18. If it was 4 to 6, it's blank to 18. What would that be?
12.
Because
6 times 3 is 18. So I'm going to scale 4 times 3 to get 12.
Nice. What if I then said, actually, I mean 3 on the right-hand side. So 4 to 6, but now I've got blank to 3.
Then I've got 2 on the left side.
Okay.
Because 3 is half of the 6.
So you go for that beginning
one.
one?
Yeah, so 2 is half of 4.
Could you also go from the 18?
Sure.
Either way. 18 divided by 6 is 3, 12 divided by 6 is 2. Cool. So far we have 4 to 6, 12 to 18, 2 to 3. Kim, no, I'm going to mention that in a minute. Hang on, just write that down. Okay, I'll mention that in a second. The last one I'm going to give you, again on the right-hand side, I'm going to say 21, and I'm curious what would go on the left-hand side.
You're saying 21
Correct.
on the right side. Then I'm going to go 14 on the left side.
Why?
Because I'm going to add the corresponding 12 to 18 and 2 to 3.
Okay. So 18 and 3 gave you 21.
Mm-hmm.
So then you're going to add the 12 and 2 to get 14. Cool. And then class, did anybody do it another? Is there any other relationships that you might could
Divine 21?
Yeah.
Mm-hmm.
It's okay if not. I always ask for more.
Can I tell you?
Yeah.
I just guessed that you were going to ask 9. So
Oh.
I don't know why. I was trying to anticipate your thinking. So let me erase that. Okay, so 21. 21.
That's awesome.
I could scale from 3.
So really, you weren't kind of actually paying attention. You were doing your own thing.
I kind of.
Should I take points off for that?
Probably. I'm not very compliant.
That's the last thing I'm going to take points off for.
Tongue in cheek. Okay.
You're playing with numbers. I love it.
Yeah. 3 to 21 is times 7.
So you could also go from the 3 and multiply by 7. Cool. All right. So far we have 4 to 6, 12 to 18, 2 to 3, 14 to 21. I'm going to lift a couple values out of that ratio table and kind of say it's as if I gave you 4 to 6.
Yep.
And I asked you X to 21.
Mm-hmm.
And this time you chose to go from the 6 to 21, but not in one fell swoop. Like we did some things to get to 21 and we did a couple different things, but I don't know. Do you have, if I were to say, put some words to what you did to get from 6 to 21, do you got any words?
I did times 3 of them and then half. So like basically from 6 to 21 is times 3 and a half. Is that what you're asking?
I don't know. I'm not sure. Is that what? Oh, because that's the half. I gotcha. Yeah. Yeah, because you got like 18 and then and then 18 and 3, and that's 3 and a half. Got it. That took me a second. Woo. Nice. And then we could say then the 4 times 3 and a half then also gives you the X, which we found was 14.
Yeah.
Cool. New problem. Well, actually, first, sorry, before we do that. So I'm just going to suggest that I gave you 4 to 6, asked you then what would be the corresponding X to 21. You found the X by scaling from the 6 to 21 and dragging the 4 along with you.
Yeah.
Okay, next problem. This time, I'm going to start with completely unrelated. Another vertical ratio table, 6 to 21. So 6 on the left, 21 on the right. And this time, I'm going to give you numbers on the left. Okay. So I'm going to say, if 6 is to 21, then what's 2? 2 is to 14. 2 is 2. That's terrible. If 6 to 21, 2 to
14.
14. And how'd you do
it? 6. Which one did you give me? 2. 6 divided by 3 is 2. Wait, what did you give me? 6 to 21, and then you gave me 2?
Uh-huh.
So divided by 3. Just kidding. 7.
Okay, so 6 to 21 and 2 to 7. Those are equivalent ratios.
Yeah.
6 to 21, 2 to 7. Cool. Next problem. I actually want 4 on the left-hand side. So 6, 2, now 4.
Now you get 14.
Okay, that's 14. Cool. I just doubled from there?
Yeah.
Okay, cool. So I'm going to lift those values out of the ratio table. So it's almost like I gave you 6 to 21. And then I said 4. No, then I said, no, I got to think 6 to 21. What did I give you? I gave you 4. 4 to something. 4 to X. And you found that X was 14. Do you notice
yeah.
What do you notice?
It's funny because towards the end of the other ratio table I was drawing, I noticed the 4 to 6, and I was like, dang it, that's only 2/3 of. So here, it's 4 is 2/3 of 6. So I need the number that is 2/3 of 21.
4 is 2/3 of 6, and I gave you 6 to 21, and then I asked for 4.
Yeah.
So did you just find 3 halves of 4? No, that's not right. What?
I said that 4 was 2/3 of 6.
Oh, so you need 2/3 of 21. I followed you now.
Yeah.
Woo. Good luck, listeners. You might have to write some of that down in order to follow some of that. So part of my point here is it's actually the same proportion. Both problems.
Yeah, I see that now.
In the one problem, we started with 4 to 6, and I said, so then what corresponds to 21? In the second problem, we started with 6 to 21, and I said, what corresponds to 4? So notice in both problems, I gave you 4, 6, and 21, and asked for the fourth value. In the one, we started kind of with the 6 and scaled to the 21 and dragged the 4 along with it. In the other, we started with the 6 and scaled it to 4 and dragged the 21 along with it.
Yeah. That's so fun.
It is kind of fun.
It is real
So
fun.
so that's an example of a problem string that I could do with kids to go, hey, when I'm given, and now very clearly, I'm writing next to each of these vertical ratio tables the proportion,
Mhm.
because I want them to be able to see, oh, it is the same proportion. Golly, I could look within and between when I'm given a proportion, and I could choose which way I'd like to go. And Kim, you taught me this. If I start going away and I don't like it, I'm going to try the other way. And I
Mhm.
might like that one worse. And so I might go back and finish the first one.
Mhm.
But we have options. And part of mathematical behavior is seeing which way you kind of want to go today, what
Mhm.
relationships are sparking for you, and kind of where you want to go. So there's,
And good heavens, it's like creative and it's interesting and it's capitalizing on relationships and it's just so much better than bat and ball. Like, honestly.
yeah. So
I,
bat and
I'm
ball is a term that we heard somebody describe cross multiply and divide, because you kind of draw the big loop
Mhm.
as the bat and the small. We're not, don't memorize that. I'll just maybe say something because it's on my mind. I was in a presentation recently, a very kind, good, let's see, good humored presenter said, it's okay if you do the tricks after you are well grounded in reasoning.
Yeah.
And I'm going to respectfully disagree. That I want to stay well grounded in reasoning, and I don't want to introduce tricks, because as
Yeah.
soon as I introduce tricks, then we just get a whole bunch of tricks. And yeah, they were grounded in reasoning, but that we're not going to hang on to the tricks, and we're just going to have more and more tricks, and kids will be able to get away with using less sophisticated reasoning. And what happens then is, sure, some kids will hang on to tricks and get answers, but what they won't do is continue to solve problems building their brain.
Yeah.
That's kind of a subtlety. Like, you might be saying, no, they're grounded. So from now on out, they can use tricks because they know what the question's asking. They can use a trick. We're done. But I'm suggesting we are missing out on the possibility of all the time that they are now using that trick. They could have been exercising their brain to get better at the kind of reasoning those problems are calling for.
Mhm.
And that's
Yeah.
kind of an important loss.
Yeah, it's a little short-sighted to to share these tricks with kids because it might give them, if kids can use the tricks, it might give them an answer today, it might give them an answer in your year, but it's not building them for future mathematics. And that's really unfortunate.
It's helping them get answers in the moment,
Mhm.
and maybe in the future, but without building. Yeah, that's well said. Yeah. So, Kim, the last one I'm going to mention is kind of similar to what I did when we talked about the sticks of gum, but now it's not a sticks of gum problem string. Now it's a rich task. And in the rich task, I'm going to lob out something that kids can think about. So I've given them enough information. Like, I might have said to them, hey, for this particular problem, you've got 12 ounces of frozen yogurt, and you put it in, and the frozen yogurt costs 40 cents an ounce, and you've put it in a waffle bowl that costs 50 cents. Can you figure out the cost of that frozen yogurt in that waffle bowl? And the kids will figure that out, and that won't take them long. But then I will then give them a problem where they don't know the number of ounces. And we've done this in a clever way in my Building Powerful Linear Functions workshop, where we've shown them the waffle bowl on a scale, but we've stuck the cup of spoons in front of the scale, so you can't see the ounces.
Mhm.
And we'll say, well, for this one that's in a dipped waffle bowl, so that's like 50 cents or 60 cents for the waffle bowl. So now we're going to add that waffle bowl 60 cents plus some ounces. Miss, I don't know how many ounces it is. I'm like, I know. What are you going to do? Is there some way you could represent all of the possibilities? And then kids usually look at you like, what do you mean? And I'm like, well, what if it was 1 ounce? And they're like, okay, so that's 60 cents for the bowl plus that 30 cents an ounce for the yogurt without toppings times one. Well, what if it was 5? And they're like, okay, that's 60 cents an ounce plus 30 cents an ounce times 5 of those. Well, what if it was 18 ounces? I'm hungry. We're getting lots of frozen yogurt. That's 60 cents an ounce plus 30 cents. And if you can see what I'm writing down, I'm writing all those in a row, so that the 60 cents stays the same. The 30 cents an ounce stays the same. What's changing? It's those ounces, because I don't know, right? So how could I represent all of the possibilities? Well, that's going to be the variable. So I'm
Mhm.
going to end up with an expression that's like 60 cents plus 30 cents times X or N, the number of ounces. And that's another way where I'm going to help students build towards the relationship between X and Y, between the input and the output. So I think we need both. I think we need good, rich tasks to get kids to do that. And we also need problem strings to really build their proportional reasoning. And together, we've got kids reasoning proportionally. It's a beautiful thing.
Mm-hmm.
Yeah, so check out Building Powerful Linear Functions, y'all. If you haven't, if registration is not open right now, get on the wait list. It might be my best work, which I'm pretty proud of a lot of what we do. So that's saying something. All right, Kim, thanks. That was fun. Thanks for tuning in and teaching more and more real math. To find out more about the Math is Figureoutable movement, visit mathisfigureoutable.com and keep spreading the word that math is figureoutable.